Good morning, friends. Now we are discussing a Venturi meter in module number 3, fluid dynamics, of the subject fluid mechanics. Derive the expression for the rate of flow of fluid through a horizontal Venturi meter. What is Venturi meter? Venturi meter is a device used to measure the rate of flow of a fluid flowing through a pipe. So we measure the rate of flow, that is how much discharge happens, that is the volume of water flown, that is in meter cube in 1 second of time, that is in meter cube per second. We consider a Venturi meter having three parts here: the inlet, throat, and the outlet. So D1 is the diameter at the inlet, that is section 1. P1 is the pressure at section 1. A1 is area at the inlet, and small v1, that is velocity at the section 1. Now we have D2, P2, A2 and V2 are the corresponding values at the section 2. So that is D2 is diameter at the throat. P2 is the pressure at throat. A2 is the area at the section 2, and V2 is the velocity at section 2. Applying Bernoulli's equation at section 1 and 2, we have P1 by rho g, that is the pressure head at section 1, plus V1 square by 2g, that is velocity head at section 1, plus Z1, that is the datum head at section 1. Similarly, I have on the right hand side P2 by rho g plus V2 square by 2g plus Z2. Since the pipe is horizontal, Z1 is equal to Z2. That means if we take earth as the datum line, the height of the pipe from the datum, that is from the earth, at both sections 1 and 2. So the same height we have Z1 and Z2. So we have Z1 is equal to Z2. So we have Z1 and Z2 gets cancels on both sides. So we have P1 by rho g plus V1 square by 2g on left hand side. Similarly, we have pressure head and velocity head on the right hand side. So grouping the similar terms on one side. So pressure head on one side and velocity head on the other side. So V1 square by 2g will become negative since it is shifted to the other side. But we know that P is equal to rho g h. So that is hydrostatic law. So from P is equal to rho g h, we have h is equal to P by rho g. So now we have h, the difference of h1 and h2, h1 minus h2. So we have here, so in place of P1 by rho g, we have H1. P2 by rho g is nothing but H2. So H1 minus H2 is H. So on the left hand side, we have H. So H is equal to V2 square by 2g minus V1 square by 2g. So applying continuity equation at section 1 and 2, we have A1 V1 is equal to A2 V2. So we have V1 is equal to A2 V2 divided by A1. So substituting V1 in the H equation, that is the H equation. So either we are substituting V2 in terms of V1 or V1 in terms of V2. So substituting V1 in H equation. So we have V2 square by 2g in place of V1 square. In the numerator, we have A2V2 divided by A1. So that whole square we have divided by 2g. So we take V2 square by 2g as common. So we have 1 in the first term. Then we have A2 square divided by A1 square. Since V2 square by 2g is taken outside the bracket. So we have V2 square by 2G. Taking LCM, A1 square is the LCM. We have this. So then V2 square is, so cross multiply 2GH of A1 square divided by A1 square minus A2 square. Now V2 is square root of this. So we have expression for V2 square here. So V2 is square root of this expression. So we have A1 square root of 2GH divided by A1 square minus A2 square. Now we know that discharge Q is equal to A2 V2, or it is A1 V1. Since we have the expression for V2, we are taking Q is equal to A2 V2. Substituting V2 in discharge equation. So finally we have theoretical discharge under ideal conditions is CD into A1 A2 square root of 2GH divided by square root of A1 square minus A2 square. So this is the discharge equation. So Q is equal to CD into A1 A2 square root of 2GH divided by square root of A1 square minus A2 square. Thank you, friends.